Alright, so in this video I'll be going over integration by substitution. Just some of the topics that this deals with are recognizing patterns, change of variables for definite integrals, integration for even and odd functions, and then I'll also talk about the U substitution. This is mostly a lot of this will be just focused around examples because most of these deal with just recognizing patterns and seeing composite functions, which is a function inside a function. So it would be something like x plus 2 squared. So notice how this is one function, but then the whole thing is a function as well. And so I'll just be discussing how you integrate things if you've got situations such as this. The first example, find the integral of x squared plus 1 squared 2x times dx. So the first thing that you want to look for in this is since you see this function inside a function, so it's x squared plus 1 inside essentially x squared, you're going to look to make a U substitution. So in this case, for your U substitutions, you're just going to use whatever's on the inside of a certain function. So in this case, it's going to be x squared plus 1, since it's inside an x squared. So just some side work. U equals x squared plus 1. And now what you're going to do next is you're going to take the derivative of u with respect to x. So du dx equals, and that's just 2x. Essentially what you're looking to do is get something on the right side of this equation right here that can match up with something that's inside your original function. So for this one, if we multiply both sides by dx, we get du equals 2x dx. So we have a 2x dx right here in our original equation. So now we can substitute in this du for this whole part right here. So if we rewrite it, notice that we replaced x squared plus 1 with u. So we can put u squared. And notice how we can substitute du in for 2x dx. So u squared du. Now you just do your basic integration. So raise your function up a power and divide by that new power. And since this is indefinite integration, you're going to have a plus c. And then what you're going to do next is just substitute back in your what you made u equal in for u. So you just plug this back into this. So your answer in this case is going to be x squared plus 1 all to the third power divided by 3 plus c. And that is the antiderivative. Next example is going to deal with the trig function. So here we have, take the integral of 5 cosine of 5x dx. This one it might be a little bit more tricky to see what we should use u for, but remember that with constants, these can just be pulled out to the front, so that front 5 isn't going to have a big impact on it. So if we rewrite it, it may be a little bit easier to see what we should make our u substitution as. So in this case we'll make it 5x, since 5x is a function that's within the cosine of x. So u equals 5x. Take the derivative, equals 5. Bring this, multiply both sides by dx. So you get du equals 5 dx. And then I guess we could have left the 5 in there, but in this case, I guess since I brought it out, we don't have a 5 anywhere else in here. So what we're going to do is just isolate dx. So divide by both sides by 5. Now we have cosine of u, and now we made dx equal to du over 5, which is essentially 1/5 du. This 5 right here and this 1/5 can cancel. So we now have the integral of cosine of u du. I'm just going to bring this around to this side. The integral of cosine of u, or the integral of cosine, is sine. Plug our u substitution back in for u, and we get sine of 5x, and I almost forgot my plus c. So there's our antiderivative for that one. Next example, take the integral of x times x squared plus 1 all squared. Once again, you can see that our u will be this right here. So u equals x squared plus 1. Take the derivative with respect to x, and you get 2x. Du equals 2x dx. Now notice how we have the x dx, but we don't have a 2. So what we'll do is just divide both sides by 2. And now we have what we need for our substitution right there. So it's now the integral of u squared times du over 2 u squared. This can be broken up into 1/2 du. Bring the 1/2 out in front, and you get 1/2 times the integral of u squared du. Move it over here. Basic integration with the u squared, so 1/2 stays the same, but bring it up a power and divide by the new power. So we've got u to the 3rd over 6. Substitute back in your u substitution for u, and you get x squared plus 1 to the 3rd all over 6, and plus c. Next example, a little bit more tricky, but once you start going about trying to solve something and you start looking at what you could make your u substitution as, then you start to see things start to correspond within the integral equation. So in this case, we're going to use sine of 3x as our u, because it's the biggest portion that's within a function. When you integrate that, you get what is that? 3 cosine 3x. You want to get your dx to the other side, so du equals 3 cosine 3x dx. We have the cosine 3x dx right there. We just have this extra 3, so we're going to divide both sides by 3. And now we're ready to make a substitution. So here we have take the integral of u squared. I'm going to split this up into 1/3 times du. I can bring this 1/3 out into the front. U squared du. Once again, just basic integration. So u to the third over 3. That becomes, if you multiply across, u to the third over 9. Plug this back into our u. Can't forget the plus c. And you get sine of 3x cubed over 9 plus c. And this will be the last example for this video. I'll have a part 2 in the next one that's going to describe definite integration with u substitutions. It's pretty much the same thing, but you just have to, there's one more critical part that you have to remember when you're doing these u substitutions and you're solving for a definite integral. So for this last one, when you're given something like this, unless you recognize something right off the bat, you're just going to want to try differentiating something and see if something corresponds where you can make a substitution. But the first thing I would do with this one is just rewrite it so it's easier to see what function is inside of what. For this one, we'll use tangent x as our u substitution, just because I've already done the problem and I have the answer next to me. So when you differentiate it, the derivative of tangent x is secant squared x. Bring your dx to the other side, and what do you know? We have a secant squared x dx, and here we have a secant squared x dx. So plug in our u right there, substitute this, all of this right here for du. Basic integration, raise the power up one, divide by the new power, add c, since this is indefinite integration. Plug our u substitution back into our equation. And there is our integral for this equation, or for this problem. So part 2, I'll be discussing definite integration with u substitutions, as well as the even and odd function ideas. 2 pretty simple concepts that make sense when you see a little picture of it.